reiterate, delta sub j of superscript L represents the error which occurs at, say, node j in layer L. For instance, this particular node, which is indexed by a sub 1 of 3, meaning that this is the node of 1 at, say, layer 3. So therefore, the error that needs to be attached or affiliated with this particular node is delta sub j of L. So this is the error that was propagated from the real end, as I mentioned before. And then further, this error will be propagating further toward the front side. And so that we do have error that's affiliated or associated with each of these nodes. And so, for example, this node and so forth. And formally, the error that takes place at each of the node is essentially representation of the partial derivative of the cost. Let's say cost that takes place from the real end is what this is. With respect to say z, which, as you can see, z here represents the sum of the weighted inputs from the previous node. So this could be considered as the change of the cost by, for example, tweaking or the changes that takes place here on of these synapses or these weights, which, because z is essentially a weighted sum of the inputs. If you consider all these a's at the previous layer, for instance, A1 and A2 of, say, layer 2 here, then this represents the change of the cost or the error at the real end as you change the amount of z. So once again, the intuition is that the delta here, as denoted hereby, represents the error at node j in layer L, which is essentially computed by this partial derivative. So once again, if you sort of like propagate from the real end, the very first one here, with respect to the error or the delta, is that the output is subtracted off by the corresponding inputs corresponding label, and then we then have delta 3, which would be the deltas that occur here at this particular layer 3, which is done by computing this representation here with respect to z. Now, this is going to be actually a little bit cumbersome process by taking this partial derivative, because the partial derivative is going to require a chain rule, which I'm going to show you at the next slide. I think that should give you a sufficient amount of detail. But further, we continue to propagate the delta to, say, layer 2 and so forth, and arrive to this this line here. Now, as far as the error that takes place here at layer 1, as you can see, there's no layer, no delta is necessary there, because, as you can see, first of all, this is the input, and second of all, there's no need to have these nodes, the input nodes, to be updated with respect to the changes of the cost, because there's no incoming, let's say, z that influences the values of the input. So therefore, delta of at the layer 1 should not be there. Okay. So essentially, we talked about, for example, of all the theta, which is the parameter that would be, in fact, be updated by using the previous value and then minus alpha times the dj ij at L. So this is the change of the delta. And by taking, once again, this the cost with respect to the parameter, and we say that the parameter, every single, all of these connections would be considered as theta of ij, as indicated by the layer, a specific layer, and that's going to be given by this using, once again, a chain rule. Now, the chain rule here, by performing, considering that this is the say the error that takes place at the very end of the architecture, at the output, for example. So for one particular sample going into for training, what is going to be required is to compute this gradient of j with respect to the each of the parameter, and by going through the chain rule here, you will arrive once again having this particular relationship, which happens to be exactly same as what we had said here, arriving to this relationship. Okay, so I presume that you could just go through each of the lines here for the derivation and arriving to this line here. Just simply going through the chain rule, and I think it can be pretty, if you can follow it well, I think it should be pretty reasonable. So I'm going to just pass and get into, once again, other elements of the artificial neural net. For example, like activation function. We talked about a sigmoidal function, which looks like this. Now, in particular, because of, by taking, say, the derivative of this logistic function or any of the activation function is going to be important because it's going to require, as part of the update procedure for as the error becomes propagated from the real end toward the front end. And so taking the derivative of each of these functions is going to be very, very important. And here for the sigmoidal function, I just want you to now know that the derivative is going to be a times 1 minus a. For the hyperbolic tangent, which I said is exactly the same as the sigmoidal function, but except that it's bipolar. For example, it starts from -1 to +1 of the big S shape. And similarly, by taking the derivative of this hyperbolic tangent function with respect to z, would give you 1 minus a squared. There's also another very interesting activation function called ReLU. Now, ReLU actually is very, very popular, and I think that's probably the most used activation function nowadays, especially with convolutional neural net, simply because it handles so-called vanishing gradient problem. It's something that we're going to talk about when we get into deep learning chapter or lecture on deep learning models. But just for now, I just want you to know that the activation function for ReLU looks like this. That is that studying, say, z, which is essentially net value. If it is greater than 0, then it's linearly rising. And if it is less than 0, then it's going to be 0. So essentially you have this so essentially you have this representation for z, and consequently, by taking the derivative of that, it's going to be equal to this. Now, remember that here, because we have 0 here, by taking the derivative of the 0, it's going to be another 0. And for greater than 0, which is linear, by taking the gradient of g with respect to z is going to be equal to 1. So it's going to become essentially a binary type of relationship by taking the first order derivative. Now, we also have something very similar to ReLU called leaky ReLU. Now, problem with ReLU here is that if z is less than 0, the gradient is going to be 0, which then is going to actually introduce a lot of problems performing computation. So rather than having a 0 there, what the leaky ReLU does is that z less than 0 is going to be given with a very small value constant times z. So it's going to be looking something like that. So on the right hand side is same as before ReLU, but on the left hand side of 0, it's going to be slightly less than 0 with some constant multiplier. The purpose of that is that if you take the first order derivative of that, it's not going to be equal to 0. So it's going to be with some very small value. So, for example, once again, when it goes through some computation, there is a chance that you might divide something with 0 for the ReLU case like here, but here you don't really have that kind of problem anymore. So this is once again ReLU and leaky ReLU would be addressing the problem having to do with uh, the vanishing gradient problem. Well, just to say that the vanishing gradient problem would occur when the number of layers is very, very many, and the error from the real end being propagated toward the front end, that's going to become problematic because by taking the partial derivative of the cost at each of these parameters, when the parameter happens to be very far away from the real end, the influence or the change of the parameter the change of the cost with respect to the parameter change is going to become very, very small. So rather than using a hyperbolic tangent or a sigmoidal function, if we use like ReLU function, actually that's going to so that type of problem will be diminishing. Anyway, so this is something that's going to be also shown as part of the deep learning model in the next round of lecture. Now, as far as deep learning or deep neural net architecture is concerned, so it really has to do with the number of layers. How many layers do you have? For example, if this is just a logistic regression, just having one layer, one hidden layer, this is considered as shallow. Even with one hidden layer here, this is also considered as shallow. Two hidden layers is also shallow. Anything that's we can say that anything that's greater than 5 or greater would be considered as deep learning. So what about if what about 3 or 4 hidden layers? Well, that's very debatable. Uh, Typically, people will say that 3 or 4 are not necessarily deep neural net. So anything that's actually greater than 5 would be considered as a deep neural net. Okay, so as far as deep representation is concerned, essentially what it's going to do is that suppose you have some sort of an input that looks like an image, then as you propagate from the left to the right toward the output side, is that it's going to begin producing a new set of features. For example, it starts off from the raw, which is the original data. So the low level features would be at the very first end of the say hidden layer, and then the next hidden layer is going to produce the mid-level features, and so forth. So as you propagate toward the output, it's going to become a higher and higher level of features. So what do we mean by low level or mid level or high level? Here's an example. So when we say low level, we're talking about like the pixel level and maybe some slight edges and so forth. But as you go toward of the same thing here, you can see that by edges connecting together, they would form a certain texture and motif. And essentially at the latter part, which is at the high level feature level, you can see actually the shape of the object a little bit more clearly. So when that happens at this level of features is when you can perform, it becomes a trainable classification or classifier. So which means that once again, by going through multi layers of these hidden layers, then the initial input data is going to be producing first of all low level feature, and then the low level feature is going to become a mid level feature, and then it's going to then produce a high level feature and so forth in sequence. Now, in terms of, let's say, a text type of, let's say, uh, description of how low level to high level would become is that the low level in terms of the text would be like, say, characters, and mid level would be like, a combination of those characters being words, and a little bit more further high level would be word group and so forth, and eventually for very high level it will be a sentence or story level. So I think that sort of like tells you or describes the intuition about these various layers of representation in terms of features. So the way how artificial neural net can be used is that it needs to go through a training cycle first. So first of all, if you have an architecture that looks like that, and then we present samples for training, and through training. Uh, so when we say training, we mean that we present samples and at the same time corresponding labels, and then we repeat this process of updating these weights until the weights or the parameters become converged. So that's if the parameters are converged, then we say that the training is complete. And the next thing that we want to do is that, so this architecture now contains a certain knowledge set. And then what we do is that we now present with a new test sample there, and then perform its prediction. So it's sort of like has these two stages. The first stage is the training part, and the second stage is the testing part. So here's an example of a MATLAB code. For those of you who's interested, very simple, three-layer model. So you could just go through, just uploading this code and just try out. For example, input could be some random value that represents, say, a certain signal, and output is also let's say it's a conversion. So suppose you have some sort of an input, let's say going like that, and then the output is maybe some certain classification. So it could be, once again, a classification of being, say, 1, 2, or 3. So you could have a number of these, you can develop a number of these data set, say a waveform that looks like that, as one having a label 1, something like that with the label 2, and so forth. And then you can sort of like go through the training and see how if the convergence actually could take place. So this is similar to the, once again, like MNIST type of representation. And I think I gave you a link where you could go and obtain some of these database, as well as the artificial neural net code to perform the training. Okay, so there are, of course, certain issues with respect to artificial neural net. One of the issues is that because artificial neural net does involve backpropagation, where the backpropagation going through the gradient descent. It's not a smooth surface like the way we've done it with logistic regression, because it's got this multi-layer propagation there. So meaning that you're going to essentially encounter local minima. Now, fortunately, fortunately, the backpropagation algorithm process itself is going to actually solve the local minima, and most likely you're going to end up having reaching to this global minimum. So this is the beauty of the artificial neural net, in that by going through the training with many cycles, you're going to actually arrive to global minimum, even though once again this cost function is not very smooth function. Another thing that I should mention is that we can also avoid the local minima and also speed up the process of convergence by implementing a temporal average direction. An easy way of implementing this is by using by emplacing, let's say, one more term, where this term is the is some constant multiplier of the previous changes of the parameters. In other words, typically when you have a change, if this is the update rule, as you know, right? So the current parameter is the sum of the previous parameter value plus the change of the parameter, where this change of the parameter is reflected by negative of the alpha times the gradient of the cost with respect to the parameter. Now this one here is going to be added with another term here, where this term represents the change of coming from the previous step or the previous iteration. So this mu here is called the momentum, which has a value between 0 to 1, and which, by the way, typically is very, very close to 1, or 0.9. So this means that as it is closer to 1, then you should have a stronger influence of the instantaneous steepest descent direction of the previous step or previous iteration. So to visually show you that momentum term, this is an example of that. For example, if you are here studying at this location, and let's say this side is the change or delta, which is what this is, whereas this one here is the change of ij at the previous step, and then the total change at the point here is the sum of these two terms, this term and this term. So this means that now, because you have we have the delta at the previous step plus the current dj d theta, that's going to be added. These two vectors are going to be added. So the sum is going to become this. So essentially, this is going to, as you can see, sort of like steer in toward the direction of the global minimum. For example, once again, suppose you are at this point. This would represent the change of the delta at the previous step. This would be representing the change at the current step. I'm sorry. That would be representing at the current step. So this would be then result of the sum of these two terms, which is going to be much better in terms of going toward the global minimum. So it speeds up the convergence, and at the same time, it's going to allow us to avoid oscillations and potentially also overcome these local minima problems. Okay, so I think this should be sufficient to again address, describe artificial neural net, or at least introduce artificial neural net with some of the steps that's important, performing the update, this update rule for the changes of the parameters in the multi-layer architecture situation. And so with that, I'm gonna now get into the deep learning model at the next round of lecture.